Hello everyone and welcome to another episode of Nuwair Yudaris. This is your host Mahmoud Nuwair. Today we'll be speaking about organic reactions. Organic chemistry will be covering SN1 and SN2 reactions and other type of organic reactions as well. Shall we get started? Don't forget to like, share and subscribe. So we're going to start with coordinate covalent bonds. Coordinate covalent bonds are formed between a Lewis acid and with a Lewis base and Lewis acid interact. So what exactly is a Lewis base? Lewis base is a electron donator and a Lewis acid is an electron acceptor. So a coordinate covalent bond is basically when one atom, it's a bond, but only one of the atoms shares both electrons and provides both electrons to the bond. Alright? You know how a normal covalent bond is one electron from each, but in a coordinate covalent bond, one atom kind of donates the electrons to the electron acceptor, as we see here. Next we have nucleophiles. Nucleophiles have lone pairs or a negative charge basically, and they are a Lewis base. So we were speaking about Lewis bases earlier. So a nucleophile likes to donate its electrons to the electron acceptor, and the more basic it is, the more reactive it is. The basic qualities of a nucleophile is determined by charge and electronegativity and the solvent itself. So an example of like some nucleophiles that donate is like hydroxide ions, ammonia, water, halide ions, and we'll be speaking about that real soon. So we have two types of solvents. We have protic solvents, which have OH or NH bond and can hydrogen bond with themselves, and these also are preferred in SN1 reactions, and aprotic polar solvents cannot hydrogen bond or cannot do any hydrogen bonding. And common protic solvents are carboxylic acid, ammonia, water, alcohol, and they hydrogen bond. Okay, they have the OH or the NH bonds, and as I said, favor the SN1 reaction. And then the polar aprotic can't hydrogen bond like acetone and DMSO and favor the SN2 reaction. So don't forget aprotic SN2, protic SN1. Alright, so these are the pKs and these are the functional groups. So pK, the kind of the lower the pKa, the more stronger of an acid it is, but it has a conjugate base. So the low pKa has is a strong acid, but does have a weak conjugate base. But the lower the pKa, the stronger its conjugate acid. So for instance, water, strong, kind of a strong acid, but has a weak base. Right? But alkane is a weak acid, but has a strong conjugate base. Alright? And then nucleophilicity, nucleophile decrease in order. So the strongest has to be iodine, and then bromine, and then chlorine, and then fluorine. So it goes this way. So iodine is the strongest out of all of them, and the more it increases, the less nucleophile affected by the protons and can react with electrophiles. They all act as nucleophiles, but iodine being the strongest, so fluorine. I would say the best way to memorize this is maybe create an acronym. An acronym I really like to use is Brown, Clyde, Brown, Clyde, Flower. Yeah, that could be a name. Or like, hello, I'm introducing myself. Cloud, I am a Brown, Clyde, Flower. Something like that. That's how you can memorize it. Electrophiles, as I was saying, are Lewis acid electron acceptors. So these like to accept the electrons that the nucleophiles are kind of donating. Alright, and these are the structures we're going to be seeing very shortly. Yep. Alright, we're going to be speaking about nucleophilic substitution reactions, the SN1 and the SN2. Alright, basically the SN1 and the SN2, we're just going to be speaking about what's the difference between them. Nucleophiles have two ways. So the SN2 occurs in one step and SN1 occurs in two steps. I know, kind of ironic since SN1 and SN2. The SN2 we're going to start with it is where it occurs in one step, like I said, and then the rate of the reaction is the K times the concentration of the substrate times the concentration of the nucleophile, and individually they're first order, but together at total it's a second order reaction. Alright, so if the substrate for instance doubles, the rate doubles. If the nucleophile triples, the rate triples. But what if for instance we have like a triple nuclei and then like a doubled what do you call it, like a doubled substrate? We're gonna have 6 here. The rate is gonna be times 6, right? And then moving on, we have the SN2 mechanism. So what is the SN2 mechanism? The SN2 mechanism is basically a strong nucleophile, alright, attacks the leaving group. So this is the leaving group. It attacks it right away. It all occurs simultaneously. So it attacks it, backside attack, and then it ends up taking its place. And it changes the configuration of the structure. Alright, it changes the configuration of the structure. And like I said, the SN2 reaction prefer aprotic solvents. It kind of prefer a polar aprotic environment. With the SN2 reaction, it prefers having a methyl over having over primary, and then over a tertiary, and over secondary, and over tertiary substrate. And what does that mean? So the SN2 reaction prefers to have an SH3 over having alkyl groups. Alright, so it prefers having this. You see how simple this is, to having, for instance, a tertiary. So I'll show you what a tertiary looks like. So this is what a tertiary would look like: CH3, CH3, and ACH3. So ask me why it prefers to have a methyl simple group instead of like a tertiary substrate structure. This is because with the tertiary structure, I'm gonna show you. So you see how there's CH3 groups, big CH3 groups taking over the structure, CH3 groups. And then in order for the what do you call it, the nucleophile to attack, alright, it needs to come from the back. Alright, but here it's bothered by CH3 groups. It needs to come from the back to attack the main chiral carbon, but it's bothered by the CH3 groups. Okay, and it can come and really knock out the bromide. So usually what a strong nucleophile does, it comes and knocks on the carbon, and it's like the chiral carbon, hey, what's up, can you kind of substitute me with your leaving group? And then the carbon is like, yeah, sure, kicks out the leaving group, and then it changes or inverts the configuration. But with the tertiary substrate structure, it's kind of hard to access the chiral carbon. And leaving groups in SN2, so like I said, the iodine, bromide, and chlorine attack backside, my bad. Then next we have a SN1 reaction, SN1 substitution reaction. With the SN1 substitution reaction, it occurs in 2 steps. Alright, so The leaving group, so for instance in here bromide has to leave first, the carbon structure tells it bye bye bromide, alright, see you soon, alright, and then kind of cheats on it, and then a nucleophile comes in and then takes its place. The carbon structure is positive, okay, and it needs some electrons, it needs some what do you call it, some electron donating group. So a new nucleophile, a stronger nucleophile comes, fills this place in 2 steps. Alright, and then the rate of the reaction is K substrate, and it's a first order reaction. Okay, so it's kindly correlated, or kindly uh, straightforward directional to the reaction if the substrate doubles and then the rate of the reaction doubles. With the SN1 reaction, it's actually the opposite though. The SN1 reaction prefers a tertiary over a methyl. So it goes tertiary, secondary, primary, and methyl. You're gonna ask me, why does it prefer a tertiary over a methyl? I'm gonna tell you that because with the SN1 reaction, the tertiary is actually more stable or more compatible with the SN1 reaction, but on the other hand, SN2 reaction, the methyl is more compatible with it. It's easier to attack the what do you call it, the chiral carbon in the SN2. That's why I prefer is like simple methyl. And then all I'm gonna say next is that the main differences between SN1 and SN2 reaction is SN1, like I said, is first order, SN2 is second order. SN1 reaction results in something called racemization of the chiral centers. SN2 results in the inversion of the configuration. So you see how in SN2, how when it attacked the leaving group and the leaving group left, the configuration changed. Here it was like behind, but here it's in the front. This is a change of the configuration. So remember, SN2 changes the configuration and occurs in one step. While on the other side, SN1, alright, results in something called racemization. Alright, there is no inversion, but a kinda, I would say there is kind of like 2 ways or 2 probabilities for attacking the leaving group, and then that's from the front side or the back side. Alright, and let's say you have a neutral nucleophile like water, and then water could attack, so you got water, H2O, attacking the nucleophile, boom boom. Alright, it can attack it from this way or it could attack it from this way, and that's what results in a racemization reaction. And then whenever you have a neutral nucleophile like SN1, it occurs in 3 steps, because in the second step you need water to remove the hydrogen. Once the water binds to it, you would have something that looks like this. Okay, you have something that looks like this, and you need to remove this hydrogen. Okay, the water side becomes positive, and you need to remove this hydrogen, so you bring in another water to remove that hydrogen. So with the SN1 reaction, they are favored by the presence of carbocation stabilizing group, but SN2 reaction are hindered by such group. SN1 reaction occur faster with substituted substrates, where SN2 reaction occur faster with less substituted substrates. Next we have oxidation and reduction. Just like simply, we're just gonna be speaking about them simply. So oxidation, or the way to memorize them is oil rig. Oxidation is loss of electrons, reduction is gain of electrons. Metals are good reducing agents, right? They're good agents for gaining electrons, and non-metals oxidize are good oxidizing agents, right? So here Mg is a metal, it gains electrons, O2 loses electrons. And then good reducing agents are LiA, LH4, and then Na, sodium, BH4. And then as you can see here, adding these reducing agents are really good to form, for instance, alcohol. So this is how alcohol and amines are performed. So primary alcohol is formed from an aldehyde, and secondary alcohol is formed from a ketone. A primary amine is formed from an amide, and then a primary alcohol could be also formed from a carboxylic acid, but it's a two-step process. And then a primary alcohol could also be formed from esters. So there are three ways a primary alcohol could be formed. Alright, remember with me, it can be formed from an aldehyde, it can be formed from from a carboxylic acid, and it can be formed from an ester. Alright, so with the aldehyde, it occurs in one step though, right? And includes a good reducing agent, KLiAlH4 or sodium BH4. Alright, but with the carboxylic acid and the ester though, it involves the addition of a water. It involves the addition of water. Okay, and it also involves the reducing agent of LiAlH4 or an ether. Alright, and that's how you create the primary alcohol. With the secondary alcohol is created from ketone. Alright, and lastly, a primary amine is created from an amide, and it's also two steps, right? LiAlH4 and a hydrogen ion or water. And that's it. And thank you so much for bearing with me. Let me know if you have any questions, and have a blessed day.